And it does a bunch of things. So that you have a compression force, pushes on the adjacent columns and may do some unpleasant things. There have been cases where it can tear a floor diaphragm apart from the axial growth. Near the corners of the floor diaphragm, it may actually crack the floor diaphragm and make it split. So some engineers believe this is a substantial effect. If you model a beam using hinge elements, you will not get axial growth. If you model using fiber sections, it will. So you have to be careful here. And this is a matter, this is not a matter of analysis. This is a matter of engineering. You know, that, in order to use nonlinear analysis, you don't have to know much about analysis. That's a problem for people like me and put in a computer program. You have to know something about analysis. You don't have to be an analysis expert. In fact, it's probably an advantage if you don't know anything about analysis. You do have to understand nonlinear behavior. And nonlinear behavior can be very different from linear behavior. I have found from working with people using Perform that if I take an engineer who knows nothing about structural nonlinear analysis but does understand behavior, he'll catch on to nonlinear analysis and deformation-based design pretty fast. If I get some young PhD that did nonlinear analysis for his PhD but doesn't know much about nonlinear behavior, he can be a pain in the ass because he requires a lot of hand-holding. The important thing is not what you know about Newton-Raphson iteration or step-by-step methods, is do you understand nonlinear behavior? And it is really, can be pretty damn complicated. Next topic, let's do the same thing for beams and shear quickly. Steel beams rarely yield in shear, but one exception would be a shear link in an eccentrically braced frame. Concrete beams are usually brittle in shear, and so usually you would want to design not for inelastic behavior in shear, but you want to design for essentially elastic behavior designed for strength. If you do allow inelastic shear, it requires a shear hinge, and it's like a plastic hinge, but it's shear rather than rotation. The demand capacity measure for deformation can be shear displacement across the hinge, or alternatively, you can actually convert it to shear strain by just dividing the displacement by the member length. If we look at a shear link in an eccentrically braced frame, roughly this is what happens up in here. You get shearing deformation in the shear link, assuming it's properly designed. And this is what the deformation might look like. And it does have some bending because there will be some bending moment, but the dominant deformation is likely to be shear. And the way in which you probably would model it would be with a stiff end zone if necessary, an elastic beam, a shear hinge, another elastic beam, and an end zone. Or you could put the shear hinge at one end. It doesn't matter whereabouts it goes along the length. It just looks better if it's in the middle. The ASC deformation capacity for this, let's look at this. Let's look at the shear hinge first. There's a number of things in this diagram. I'll come back to this in just a moment. If you look at the shear hinge, the plastic shear strain for yield and shear, and this is an adequately stiffened shear link, would be 0.5% for IO, 11% for life safety, and 14% for collapse prevention. That's a pretty big shear strain. So it's pretty generous. It's also necessary because these tend to be fairly short. The shear displacement is shear strain kind of the clear span length. But what if you have inelastic bending as well as shear? What I've got here is two things. The right-hand end first is a moment hinge. And this would be, if you think the shear link can yield in bending, and if a long shear link might do that, then you probably should model for bending and you could put in a plastic hinge. That's one thing you might do. Or working backwards, if you intend that the shear link yield only in shear and does not yield in bending, what you might do is put in a moment strength section, then calculate the strength on that just to make sure that the strength demand capacity ratio is less than 1, which means a hinge does not form, a moment hinge. And if the demand capacity ratio is larger than 1, then a plastic hinge does form. This is not what you intend. You need to redesign your shear link. So this is the way in which you might model this, end zone, elastic beam, shear hinge, elastic beam, possibly a moment hinge, end zone, and then you might separately put a moment strength section at this location. In a concrete beam, sort of similar. You might have an end zone, a plastic hinge, elastic beam, a plastic hinge. And if you are, in the unlikely event you would allow inelastic shear deformation, you could put a shear hinge at the end, which is probably where the shear where shearing deformation is likely to occur. If you did not want shearing any inelastic behavior in shear, that would be the OR. You could put a shear strength section here, calculate the shear strength demand capacity ratio. If it's larger than 1, it indicates in fact a shear hinge would form. That's not what you want. You have to redesign your beam. There's a complication, is that the larger the hinge rotation, the smaller the shear strength. And again, I think you can see this intuitively. If you have a rotation at a hinge, it's going to degrade the shear strength. And it tends to look something like this. This is your shear strength capacity versus the hinge rotation demand. And it's one of many complex interactions that can occur. It's one of the biggest complications in nonlinear behavior, these interactions. This is one example. In Perform, you can consider this. However, you can only consider it for a shear strength section. You cannot consider it for in the current version of Perform for a shear hinge. And I'll illustrate later on how that might be done. Let's look at this. Let's see how beams can be modeled using Perform. And all I'm going to do is look at some compound components here. Let's look at a chord rotation model. And I hope you can read this from back there. It consists of an end zone, a FEMA beam, and FEMA beam implements the chord rotation model. And there are two of them. And the reason is that they could be different strengths. In this case, they're not. They're the same. But they could be different. So you have one for the left end, one for the right end. And then you have an end zone at the other end. That's the simplest model. You might also have a plastic hinge model, an end zone, which lights up yellow. I hope you can see that. And then a plastic hinge, then an elastic beam, and another plastic hinge, and an end zone. But you now have to come up with a plastic hinge rotation and capacities yourself because ASC 41 doesn't give it to you. It's actually quite easy to get it for a concrete beam, a little more difficult for a steel beam. Here's a plastic zone model, and this is one which is using a curvature hinge. And this is actually just a very simple one. This now it's not a rigid plastic hinge anymore. This is something where you specify a moment curvature relationship for the hinge. Now, I'm not going into the details. It's just a little variation on a rigid plastic hinge. But this one has got an end zone. Then it's got a short length of beam, and this is 6.73 inches long, which happens to be 1/4 of the beam depth. This is W27 by 94. So we're putting a curvature hinge at the middle of the 0.5D length, and these lengths are not to scale because right now I don't know what the span of the beam is. All I know that it's got some components. And then an elastic beam section, another curvature hinge. And the other thing about this is the curvature hinge has got a tributary length. And it would take me a little while to explain this, but basically it says that this 13.46 is 1/2 the depth of the beam. So it's actually saying, let's use a plastic zone here with a moment curvature relationship designed by this hinge. And let's make this plastic zone 1/2 the depth of the beam. So you position it 1/4 the depth out, you assign a tributary length 1/2 the depth, and you've got a plastic zone model. Next thing we can use is a plastic zone model with a fiber section, and here there's a short length of fiber section, which is now 13.46 inches, 1/2 the depth of the beam, and this is using a fiber cross section. And if you want to show the properties, this happens to have just 4 fibers, 1 for the flange, 2 for the web. and 1 for the bottom flange. You could use more if you want, but 4 probably is not a bad idea. The next one would be a finite element model, again using the same fiber section, end zone, and then some finite elements of different lengths, 6 inches, 13.5 inches, 27 inches, and 54 inches, and then the elastic beam in the middle is whatever is left. I don't know what the span is presently, so the elastic beam in the middle would be whatever is left. This would be a finite element model. And here's an example where the shear strength depends on the rotation. This actually is the end zone is a plastic zone model with the fiber beam section. And if I go to the strength section, what I've done is define a shear force strength section. And it just happens to be rather crude. It's got a strength of 100, and actually the strength can depend on the axial force, so don't worry about that. What I'm interested in now is if I look at the strength section, it says the basic component for effective rotation on shear strength is from 2 to 2. Now I'm going to go back to this strength section and look at the rotation effect. I've specified some properties here, and let's not worry about the details. Just look at this diagram, which indicates that I can specify a shear strength factor which depends on rotation of an adjacent hinge or plastic zone. I've specified some rather arbitrary values here. Don't worry about the details. But you can specify properties which will modify the strength of the beam depending on the amount of hinge rotation. And when I come back to this model, what this is saying is that for this, let's do the first one. For this component, use the rotation from component number 2 to component number 2. I go back. Component number 2 is the inelastic fiber section at the left-hand end. So what it is saying is when you come to calculate the shear strength capacity at this cross-section, look at the current amount of rotation over this plastic zone. Using that rotation, go into the little diagram I had before, calculate the strength reduction factor in shear, apply that to the shear strength to get an effective, a reduced shear strength, and calculate the demand capacity ratio based on that reduced shear strength. It's just something that, it's an important effect. You could do it by assuming the worst case, and you could specify a shear strength reduced by the worst worst hinge rotation you might expect, but this is a little more sophisticated. It will actually include the hinge rotation effect for you. Next topic is modeling and demand capacity for columns, and I'm going to talk mainly here about modeling. The basic models are exactly the same as for beams: chord rotation, plastic hinge, plastic zone, and then finite element or exact theory. Chord rotation is probably the one you'll use most of the time. However, the behavior is complicated by P-M-M interaction. And a number of things happen when you get PM interaction. The moment strength depends on P and vice versa. You know that. I'll show the interaction surface in just a moment. We now have biaxial bending rather than uniaxial bending as in a beam, which is a complication. And most important, after yield occurs, after a plastic hinge forms, what does it do? It doesn't simply rotate. It's much more complicated than that. The shear behavior is also more complicated. You've got biaxial shear, and the shear strength can be affected by axial force, by moment, and also by hinge rotation. So let's look at your PM interaction survey. You're familiar with these. I'll just show some implications of these in just a moment. If we look at a steel beam, and we take just a short length of the beam, we can get a PM interaction diagram, which looks something like this. If the PM point is inside the interaction or yield surface, then the column is elastic. If it reaches the surface, then a plastic hinge forms. And the problem is, what happens when a plastic hinge forms? We'll talk about that in a moment. Concrete's a little different. You get an interaction surface that looks like this. Let's look at a steel section. Just look at some simple aspects of inelastic behavior for a steel section. Again, it's a short length of beam. Pure moment, this means that you're increasing the moment out here. A hinge forms at this point, and it's just a moment hinge, just like a beam. If you have pure axial force, you're increasing the axial force. When it yields here, it forms an axial hinge. A little bit of complication though. Suppose you had just a tiny bit of bending moment to the left, then actually this flange will yield first and this one won't, so actually it'll start to rotate. And if it's a little bit to the right, it'll rotate in the other direction, so it's very sensitive. And you will not get an axial hinge like this because you generally can't accept axial forces of that magnitude in a column. But theoretically it can happen. So it's like an axial hinge. And if you have a combination of P and M, when you reach here, in this particular case, if you have P and M as shown, this flange will yield, this flange will stay elastic, so you'll get both rotation and axial deformation at the hinge. It's sort of interesting if you have a zero-length hinge and you get axial deformation on a zero-length hinge. How can that be? You know, it intuitively a little strange. It means infinite strain, but it really isn't that strange. If you have rotation on a zero-length hinge, that's infinite curvature. And infinite strain, infinite curvature, not really that much difference. If you cycle the inelastic behavior on a steel hinge or a steel short length of a steel member, let's increase the axial force to some value and then cycle the bending moment backwards and forwards. So you increase the axial force. When you cycle a moment to the right, this flange will yield. When you reverse the moment, everything will unyield, and the next thing will happen is that at point 2 here, this flange will yield. So when this flange yields, you get some shortening. When this flange yields, you get some more shortening. Cycle it backward to point 3. This flange yields still some more shortening. Cycle backwards to 4. This flange yields still some more shortening. It just progressively shortens if it's in compression. If it's in tension, it progressively elongates. So this is just one of the things that can happen. There is a method for analyzing this, and it's known in the academia as plasticity theory. It actually originates with the von Mises theory for yield of a steel material, and it's applied by analogy to a PM interaction surface or a PM yield surface for a steel column, and it works quite well. It's pretty good for steel. I can't go into it. There is in the notes, there's a discussion of plasticity theory you can read if you wish. Concrete section, similar kind of thing. I'm not going to go through it in so much detail, but now if we just increase the bending moment, what happens is the neutral axis shifts towards the compression side, and so there is some axial extension. So even with no axial force, there is some axial extension. If you were to increase the axial force to the balance point and then increase out to here, then you would get only rotation without any shift of the neutral axis. So this becomes rather more complicated. Now, the reason why this happens in a reinforced concrete column is not because there's plastic behavior, it's because there's cracking. And plasticity theory applies if you have plastic behavior, and it doesn't apply to cracking. So strictly speaking, although you can apply plasticity theory to this type of PM interaction surface, you really shouldn't. However, we still do. And it's, from a practical point of view, it's probably not bad, but it really, strictly speaking, is not correct. So if you look at PM models for column elements, each model, and I'm talking here about a hinge model or a plastic zone model or a chord rotation model, are all the same. You need two FD relationships, one for bending, one for axial force, and the linkage between the two is through plasticity theory. Chord rotation model, you have an end moment versus end rotation, which is just like for a beam, and axial force versus axial extension or shortening. Plastic hinge model, hinge moment versus hinge rotation, hinge axial force versus axial deformation on a zero-length hinge, which may seem a little strange. Plastic zone finite element exact models, moment versus curvature for bending, axial force versus axial strain, incidentally measured to the cross-section centroid for axial force. And if you use plasticity theory, you can link them together. An advantage of fiber section, we'll see later on, is it doesn't need plasticity theory. Column deformation capacity. Because of PM interaction, column hinges or plastic zones have both axial and bending deformations. But the deformation demand capacity measure uses usually only the bending deformation, just the rotation. You don't worry about the axial deformation. Your capacity is based on the rotation. A complication is that the bending ductility is smaller if the axial compression force is large. So the hinge rotation capacity depends on the axial force. And the second complication for reinforced concrete columns is it also depends on the shear force. And to some extent, Perform allows you to do this. I won't go into the details. ASC 41, concrete column capacity, gives bending capacity for chord rotation model only. And the way in which the rotation capacity varies is roughly shown in this diagram. This is the rotation capacity, and this is axial force. If you have low shear, then at zero force, this is the rotation capacity, and for a high shear force, it's 20% smaller. These are the values you would have for a beam. Those values apply out to P over 8 A sub G F prime sub C of 0.1. Then they start to decline, and for larger axial forces, you have rotation capacities about 75% of the beam values. And for details, take a look at ASC 41. An alternative plasticity theory is a fiber section. I've already talked about fiber sections a little for beams. The advantage of a fiber section in a column is that PM interaction is taken account through the behavior of the fibers. You don't have to use plasticity theory. Another advantage is that since it doesn't use plasticity theory, it also applies for a concrete column as well as a steel column, because it does model the cracking correctly. Shear in concrete columns, it gets a little more complicated than a beam. You're still going to have shear hinges, but they're a little more complex. Firstly, you have shear in two directions, and so you have an interaction surface. It may be circular, it may be elliptical, it may be some other shape. You have some control over the shape within Perform. The shear strength can depend on the axial force, and the shear strength can depend on hinge rotation. So you could take in some of these complicated interaction effects. So it's somewhat similar to in a beam, but with these added complications. Sort of models you might have for a column with shear. The one on the left here is where the shear must be elastic. You would have a PMM hinge at each end, or maybe FEMA column components, and you would have shear strength sections. It's supposed to remain elastic and shear. You put in a strength section, calculate the strength demand capacity ratio. If it's less than 1, it doesn't yield in shear. If it's greater than 1, you've got to redesign the shear. If you want to have inelastic shear, then you put in a VV hinge, and you might also have moment hinges as well. Perform has a shear hinge with interaction, but it doesn't have axial force effect and shear effect and things like that. I'm sorry, it just has basically a fixed shear strength. It's unlikely, though, I think, that you would have inelastic shear in a concrete column. It's just not a good idea. Beam to column connections. Firstly, let's look at a beam which has got some end connections, maybe a bolted connection which is semi-rigid, or perhaps a pre-Northridge welded connection which may fracture. Sort of thing you might do one thing is you can use a semi-rigid moment connection. I'm talking here about Perform. It's got a semi-rigid moment connection which has got a moment versus rotation relationship like this. You might use this for, say, a semi-rigid bolted connection of some kind. You would have to know the moment rotation relationship for the connection, and you would put in a component here which does this. An alternative would be to put in a short, and this would be for the fracturing cross-section, a very short, say 1-inch long plastic zone with fibers which model brittle fibers for the flanges and ductile fibers the web. I'll give an illustration of this in just a moment. And you might, in addition, also put in a plastic hinge if you like. So you can do that. You can sort of mix and match these components in different ways depending on what you think is necessary. If you look at a fiber section for a fracturing connection, you might make this length here just 1 inch, just because it has to be a finite length. This is the depth of the beam. And notice that if a flange fractures, it'll rotate about the other flange. So the tension strain out in this fiber is basically a connection rotation times the depth divided by the length. Don't worry if you're worried about that, forget it, don't worry about it. The important thing is this other diagram. For the flange, the way in which you can model and perform is with a concrete fiber to provide the compression. It's just because a concrete material is a compression-only material. That models compression, probably make it very strong in compression. For tension, you could use a tension-only fiber, which has a very small ductile range and basically fractures. And this would then enable you to model a fracturing weld at the flange. For the web connection, which is more ductile, a more ductile yielding material, and you would do this using a fiber section. Connection panel zones. I think you're probably familiar that the loads on a connection panel zone is basically you've got moments and shears coming in from the beams, moments and shears going out of the columns, and basically moment is being transferred from the beams through the panel zone to the columns, or vice versa. The effect of this is it puts the rather large shear stress on the panel zone. Much larger shear stress and strain in the panel zone than in the adjacent beams and columns, and in fact in the opposite direction. And you get a distortion which looks like this, and so the angle between the beam and the column no longer remains at 90 degrees, and it acts somewhat like a semi-rigid connection. Panel zone modeling.